So here's something that's a little bit of an extra for 1.2. In 1.2 we talked about characteristics of polynomial functions, and this is basically a formula that we can use to help us figure out, say, a constant finite difference, a leading coefficient, or the degree of a polynomial. Okay, so what exactly are all these? The constant finite difference is, if I just go back to our warm-up from 1.2, it's these guys right here, the 48s. Those guys are considered the constant finite difference, and that would go at this end of the equation right here. Now your leading coefficient is your a value at the very front of your polynomial function. Okay, and the degree would be, in this case, for the 48, it would be a degree 4. Okay, now that exclamation mark in the equation right here is called a factorial. So what that means is if your degree is 4, then you would go 4 times 3 times 2 times 1 until you get to the 1. So for example, if this was like 7, this bracket would be 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay, so that's how a factorial works. All right, now example number 1. State the degree of the polynomial function that corresponds to each constant finite difference. Determine the value of the leading coefficient for each polynomial function. So A, if you have the fourth differences, and then they're all negative 24s as their constant finite difference, I'm going to put that in this part of the equation. Remember, it goes right here as a constant finite difference. It's equal to your leading coefficient, which is what we're trying to find. And since they said it was the fourth differences, then that must mean that it's a degree 4 polynomial. So that's 4 times 3 times 2 times 1. Remember, that's how the factorial works. So all those multiplied together equals to 24. So 24 LCs is equal to negative 24, which means I divide the 24 on both sides to cancel that out. That means my leading coefficient must have been negative 1. So I'd have this entire polynomial, and at the very front of the polynomial, in front of that x to the power of 4, I would have an a value of negative 1. So let's try that again a couple more times. This is our constant difference right here, so we're going to put that right there in the equation. It's a third degree, therefore is 3 times 2 times 1. And then we're trying to find the leading coefficient. So 3 times 2 times 1 is 6. We're going to divide that out on both sides, and we get a leading coefficient of 2. So this is our a value of positive 2. Okay, here's our last example for finite differences. The table below represents a polynomial function. So we want to use finite differences to determine the following. I've calculated all the finite differences for 3 rows, and I've noticed that this last one has constant finite differences. So this one must be a third degree, which means that it's a cubic function. And then in order to find the value and the sign of the leading coefficient, I'd actually have to use that formula we just learned. So if I go down a little bit, I have the equation right here. So your constant finite difference, which was 6, because that's one that keeps repeating, is equal to leading coefficient times the degree of the function with that exclamation mark. So 3 times 2 times 1 is 6, and then I'm going to divide the 6 out on both sides to solve for my lowest common denominator. Okay, our leading coefficient. So that's going to equal to 1, which means the value of the leading coefficient is 1, and then the sign of the leading coefficient is a positive 1. Okay, so that was just a little bit extra on finite differences.